good morning or afternoon depending upon when you are listening to this set of lectures. My name is Vijay Kumar. I am here at the Electrical Communication Engineering Department of IISc Bangalore, and I will be leading you through a course on error correcting codes. So, this is a course that is a first introductory graduate level course. Okay. Okay, so that is the title of the course, and this is our first lecture. So, I am going to call this first lecture course overview and basics. So, I am taping this first lecture having taped the remaining lectures in the course. So, that gives me an opportunity to tell you about the course with a better knowledge of how things unfold from here onwards. So, as it turns out, what we have done is we have gone ahead and taped about 42 lectures, and let me just quickly take you through the course as it is going to evolve. So, here is the course outline, and what I have done here is that so these are the first 15 out of the 42 lectures, and you see the various titles. So, the way the course actually proceeds is vertically down and then over here. So, we start with basics of block codes. So, just by way of clarification, when we talk about codes here, we are going to mean codes that are used for error correction. So, this is distinct from say source coding or cryptographic coding. Okay. So, we are interested in codes primarily for the purposes of error correction, and so some of these titles may not mean too much to you. We will first talk about at this moment, but you can revisit this later. So, we will go through the basics of block codes starting from today. After that, so this is I think one of the I feel it is one of the good things about the course that I actually take you through the mathematical preliminaries. That is, because I do not really assume too much by way of background, but you will need background as you progress through the course. So, we cover groups, we will cover rings, we will cover fields, we will also talk about vector spaces. Okay. So, that is delving into linear algebra. We will talk about vector spaces, we will talk about notions of linear independence, basis and dimension, because these are concepts that we will draw upon throughout the course, and I did want to make the course self contained. So, as you can see here, we spent about 3 lectures talking about groups, rings and fields. So, maybe I can enlarge it a little bit better. So, we do spend about 3 lectures talking about groups, rings and fields, that you can see this is the block here, and then after that we go on to talking about vector spaces. So, that is the linear algebra, and the number at the bottom in brackets represents the number of lectures that we will actually end up spending on each of these topics. Then after that we will talk about a subclass of codes, and as in any other subject, the linear case is the one that is most tractable, and as it turns out it is also quite useful. So, we will actually spend a fair amount of time on linear codes. Then we will talk about bounds on code size. It turns out that you can rank codes according to certain performance criterion, and one of them is the code size, and there is another parameter that will come up later. So, this is code size in terms of the other parameter, how good can your codes get. So, we will spend 2 lectures on that. Then after that we will turn to the topic of decoding, and there is a way to actually optimally decode a linear code. It is called standard array decoding. Now, throughout this part of the course we will actually be working with binary codes, that is we will be working with codes whose symbol alphabet is either 0 or 1. Okay. So, I think another feature that I am that these lectures keep in mind is that we introduce the math only when you need it. So, finite fields are used to discuss block codes, but what I am going to do is I am going to introduce finite fields towards the tail of the class rather than now, because these concepts can be passed on without need for finite fields. Then after that, now moving to the latter part of the course, okay, lectures 16 through 42, what we will do is we will first talk about convolutional codes. Okay. So, these are distinct from block codes, turned out to be very useful in practice. For example, these codes were used in deep space missions also. So were block codes, but convolutional codes had some aspects in which they perform better than block codes, not all. Then after that, so we spent 5 lectures on convolutional codes. Then we spend time on something which is I have given the name generalized distributive law, and the reason I have called it that is because I have taken the title from a certain journal article. Now, this is I think perhaps a unique feature of this course. Here what how did this come about? This came about because coding theory actually transitioned from a time period in which the techniques that were employed to build codes were largely algebraic in nature, with perhaps the exception of convolutional codes. But then sometime in the 90s, around the early 90s, there was a new class of codes that came into the picture which turned in excellent performance, but whose description was in a sense more probabilistic and using probabilistic techniques as opposed to algebraic. So, it is not to say that there was no algebra, there is algebra, but it was more probabilistic in nature in comparison with earlier codes. So, what I am speaking of is the difference between turbo codes, which are a recent invention, compared to let us say BCH or Reed-Solomon codes, which were the traditional class of codes. Now, those codes, the strength of those codes was not that they were better codes in terms of their inherent structure. They were better codes in the sense that they could be decoded more easily. So, in practice there is a great deal of emphasis on ease of decoding, and this is where turbo codes and their successors known as LDPC codes, LDPC standing for low density parity check codes, score heavily. Now, at least now this is a personal decision. I found that the theoretical underpinnings become a little bit clearer when you adopt the viewpoint that is taken in a very nice article entitled the generalized distributive law, which basically tells you that there is a method of decoding which follows I mean there are very many different names that are associated with this style of decoding. Someone might say this is an iterative decoding, others might say this is message passing decoding, others might say this is belief propagation, but whatever that phenomenon is or the method of decoding is, this title, which is somewhat mathematical and in nature and might scare you, actually gives you a very nice introduction, and it is what it provides what I think of as the theoretical underpinnings for the methods of decoding that I use today. Then after that we talk about the class of codes that use this particular distributive law. There are 2 classes primarily, although there are others, turbo codes and LDPC codes. Here we will cover LDPC codes. They seem to be fast becoming the ubiquitous code of the present day. That is, anyone who needs a code for any application will often, the first code that they will think of are LDPC codes or some variation of them. Okay. Now, so in other words, this class of codes really represents the modern class of codes. In fact, there is a book on coding theory which is devoted to the theory of codes such as this. Then after that, so we spent 7 lectures on that. Then we go back to the algebraic viewpoint, and we now talk about codes whose algebraic structure draws upon more theory than we have covered up to this point. So, we actually delve into the theory of finite fields, and finite fields are good for constructing very many classes of codes. What we will cover in this class are a class of codes known as cyclic codes, and although the number 3 might look small here, actually these lectures are somewhat lengthy. So, as a number count is probably stands for more than 3 lectures, because I actually use written material and I go through it a little faster than in the earlier lectures. So, there is a fair amount of material in this block. Okay. So, with that we actually end the course. So, again, so we start with basics, which involves block codes. Then in the middle we go off to these codes having a probabilistic description, and then we come back again to block codes and discuss the ones that involve more algebra. Okay. So, that is a quick outline. Now, before I forget, this course does have a list of homework problems. They are not really tied into the lectures in as in this lecture requires you to solve these problems. They are just a list of problems, and as you roll through the course you can look at the problems and see if you can try them. So, that might give you that might help you in getting a feel for how well you understood the course. Now, another thing which you might find useful is here in a file, and I think I will actually come back in a later lecture to show you actual textbooks in the class, but I thought it might be useful for you to actually look at a list of textbooks. Now, there are a large number of books on coding theory. This was not the case some years ago, but in recent years there have been a large number, and many of them are very good. So, it is a matter of taste, and some emphasize the algebraic aspects of the subject, some and a few emphasize the probabilistic aspects, and but I have tried to list and this list is by no means exhaustive. There are very many good books that are not listed here, and I have also listed a chapter that we actually had written on error correction, which applies which appears in a handbook, and this course follows somewhat along the lines of that chapter. And here are some 3 of the journal articles that I am actually going to draw upon in this class, and including the article on the generalized distributive law. Okay. So, that is your references, and I have also told you about the homework. Okay. So, with that, what I am going to do is I am going to start taking you through the basics. Preliminaries that will allow you to better understand binary codes, but first a few words about where these codes are actually going to be used. So, these codes will be used over a communication channel, okay. And so let me put that down here. So, there are 2 example communication channels that I will put down here. Okay, so there are two example communication channels that I have presented here, and this here is the binary symmetric channel. So, and this may be familiar to you as maybe this. So, there are two inputs which you can regard as 0 and 1, and the outputs are also 0 and 1, and this epsilon is the crossover probability, that is, it is the probability of transmitting a 0 and receiving a 1 or vice versa. Then the second channel is what is called an additive white Gaussian noise channel. Here the input to the channel is what is transmitted by the transmitter, which is S, and then a noise is added to it, which is N, and what you actually receive is R equal to S plus N. This is called an additive white Gaussian noise channel. The additive is clear from the picture. Gaussian, because the noise is assumed to be have Gaussian statistics. In the deep space channel, for example, you might encounter channels like this, and although channels may not exactly look like this, this is the channel for which codes are most often designed. Now, you might ask, where would this channel come in? You could argue that, for example, in magnetic recording channels, the channel might be better modeled as being this type of a channel as opposed to this, because you might be recording zeros or ones. But there is another connection, that is that if you quantize the output to two levels, then what you receive could be construed as being 0 and 1. Now, as for the input, well, when you send a message, you are typically going to use some kind of modulation. So, even though this channel can accept any real input, it is customary from the point of view of simplifying the hardware to use a modulation with a finite small alphabet, with some example popular alphabets being binary phase shift keying BPSK, or quaternary phase shift keying QPSK, or you might use 16 QAM for that matter. So, these are some example modulations. There may be some slight differences because I have shown a real channel here, whereas typically when you talk about a QAM constellation, you would use a complex version of this, but that is more a matter of technical detail. But consider the case when the input is BPSK, when your S. Now, this channel model abstracts some details that you would see, for example, explained in a course on digital communication. So, this is the baseband, equivalent baseband model. So, in the equivalent baseband, the transmitted signal would be either plus or minus 1. Okay. So, that is where your binary input would come from, and if you quantize the output, you would get binary output. And if you relabel the binary input as 0 and 1 and relabel the binary output after quantization as 0 and 1 again, then what you have is a binary symmetric channel. And in the early days, coding theorists focused on this binary symmetric channel, and you do lose something in this because no matter if so the input assumption is not too bad, because you might actually be transmitting binary input, but at the output, if when you quantize the received signal to extract a binary output, you lose some information in the process, and that costs you something. And so, in the early days, they made the quantization assumption just to make the problem more tractable, but they did pay that penalty. And one of the benefits of the subsequent probabilistic approach is that that approach enabled them to work with codes that could work off the real output of a channel as opposed to the quantized. So, the algebra was well tuned to this channel, whereas the probabilistic methods can also work with these channels, and that gave them an important advantage in practice. Now, what I would like to do is just go through some basic math that you would need to work with binary signals. So, I will introduce first some notation. Okay, by the way, another point I want to mention is that these lectures are going to be written out on Windows using Windows Journal on the tablet PC, and so the plan is to make available on the website where you find the course video a PDF file which has all the lectures in PDF form. Okay, so that I think would be useful. So please keep that in mind and look for it on the website. There should be a file which has all the lectures appearing as a single PDF file, and I will try to append to it the course outline, the list of references, and the homework as well. Okay. All right. So getting back to the math here. So here, what we see are rules that we will use to add and multiply when the alphabet just consists of 0 and 1. So this is addition, which corresponds to exclusive OR or addition modulo 2, and this is multiplication, which corresponds to the AND operation. We will write F2 for the alphabet 0 1, and now I want to introduce another notation, F2 to the n, which is the collection of n tuples, that is vectors with n components, and so we use the superscript here to denote that. For example, when n is 2, then F2 to the 2 consists of the 4 vectors So in general, from this it is clear the size of f to the n is 2 to the n. So we will need the simple notion of Hamming weight. So supposing you are given an n tuple, that is a vector with n components, x, then the Hamming weight of that particular x is simply the number of non-zero components. Now remember that the components of x are either 0 or 1, right. So for example, if x is 1 0 1, then the Hamming weight is 2. Okay, so here we are looking at properties of the Hamming weight function. So, the first property is that the Hamming weight, since it simply counts the number of non-zero symbols, it is always going to be greater than or equal to 0, and the only way it can equal 0 is if the vector is the identically 0 vector, that is the vector or n tuple with all the components are 0. The second property is that if you take the sum of x plus y, then the Hamming weight of that sum is less than or equal to the sum of the Hamming weight of x plus the Hamming weight of y. And that is actually not hard to see why that is true. First, let us take a look at an example. So, in this example, x is the vector 1 1 0 1 1, y is 1 0 1 0 0, and if you add x and y, you get z, which is 0 1. See, 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 0 is 1. So, here the Hamming weight is 4. This has Hamming weight 4, this has Hamming weight 2, but z has Hamming weight 4. And the reason for that is clear, because whenever you have two 1s facing each other in the same position and you carry out addition, then their sum is 0. So, in some sense you lose two 1s. So, the Hamming weight of the sum can never exceed the sum of the Hamming weights, but typically it will be less by a factor or term which is equal to twice the number of 1s they have in common. For example, the positions in which these two vectors have 1s in common is just the first position. So, the weight is 4 plus 2 minus 2 times 1, which is 6 minus 2, which is 4. Okay. But anyway, the thing that you have to keep in mind is just that the Hamming weight of the sum of x plus y is less than the sum of the Hamming weight of x and the Hamming weight of y. Next, we will introduce a related concept, that of Hamming distance. Okay. So, the next concept is that of Hamming distance, and the Hamming distance, if you have two vectors x and y, and both let us say are binary vectors having the same number of components, then the Hamming distance between them is Formally speaking, it is the Hamming weight of their sum, but most people think of it as simply saying the Hamming distance between x and y is simply the number of components in which they actually differ, because that will end up being the Hamming weight of x plus y, because Hamming weight of x plus y counts the number of non-zero symbols in x plus y, and that is precisely the symbols corresponding to locations where x and y disagree. Okay. So, in this example, so we are back to the same example, x and y are the same as before, and here we saw that x plus y was 0 1 1 1 1. So, the Hamming weight of this is 4. Now, the Hamming distance between them according to this definition is the Hamming weight of this, but you can also just see from inspection that if you look across these two vectors, then they basically agree in just the first position, everywhere else they differ. So, the Hamming distance is 4, and that is typically the way people think about it. Okay. So, we introduced the notion of Hamming weight and we looked at properties of the Hamming weight function. So, now we have introduced Hamming distance. So, we will again investigate properties of the Hamming distance function. Okay. So, the properties that the Hamming distance function actually satisfies are that the Hamming distance between any two vectors is strictly greater than or equal to 0, with equality holding only if, in fact it is if and only if x equal to y, because the only way that x and y, well, the distance greater than being greater than or equal to 0 is obvious, because you are counting the number of locations in which the two vectors differ. So, that is going to be a number that is greater than 0, and if it is 0, that means there are no positions in which they differ, which means they agree everywhere. So, the vectors have to be the same. So, the first property is clear. The second property says that whether you look at the Hamming distance between x and y or y and x makes no difference, and that again is obvious, because you are just looking at the pair and seeing in every location is the pair the same or it is different. So, the order is irrelevant. The third one, more interesting, is called the triangle inequality, and the triangle inequality states, well, from a mathematical point of view, it just says that the Hamming distance between x and z is less than or equal to the Hamming distance between x and y plus the Hamming distance between y and z. But pictorially you could actually look at it like this, that is that just like the distance in the real world, in everyday world, from x to z is going to be no more than the distance from x to y and y to z, the same is true of the Hamming distance function. So, the Hamming distance agrees with our Euclidean notion of distance, and it turns out that this is useful because it allows you to carry over your intuition from everyday life into the Hamming world, at least to some extent. Okay. And the reason for this is actually very clear, but I am going to illustrate this on the next page with an example. Okay. So, let us take our vectors x and y to be as before, but now in this example there is a third vector. So, let us say that that is z, and let us look at the Hamming distances between the three pairs. So, the distance between x and y counts the number of symbols in which they differ, right. So, they agree on the first, they disagree in 2, 3, 4 and 5. So, from that we say that the Hamming distance here is equal to 4. Now, between y and z, this has 2 ones, this has all ones. So, it is clear that the distance is 3. The distance between x and z on the other hand is just 1, okay, because they only differ in the this. So, now the theorem just says that the distance between x and z is less than the sum of the distance from x to y and y to z. So, that seems like a gross overestimate in this case. Okay. But sometimes you could have equality, and the reason for that is not hard to see. I mean, the reason why this distance will be less, because you could go from x to z by first flipping some of the symbols in x, which will take you to y. For example, you can flip the last 4 symbols and get to y, and then you can flip the second, the fourth and the fifth symbols to get to z. But some symbols you flip twice. In fact, 3 of them you flip twice for no reason, and for this reason, that in some sense that is wasted effort. You could have just flipped 1 to go from x to z. So, from this it is clear that the Hamming distance between x and z is going to be the less than or equal to the sum of the distance from x to y and y to z. Now, I have shown the arrows in this way, but you could argue in just about any regardless of the orientation of the arrows. So, for example, if you look at it this way, then this would tell you that the Hamming distance between y and x is actually equal to the sum of the distance from x to z and z to y. Okay, so, here is an instance in which you actually have equality. So, that ends our mathematical preliminaries in terms of Hamming weight and Hamming distance. Now, we want to talk about block codes, that is, we want to talk about objects which can actually be used for the purposes of error correction. We will begin with a very surprisingly simple definition, and then I will explain why it is that that works. We may not, and then we will see examples in the next lecture, which will make the concept clearer. Okay, so we have as I said, a simple definition of a binary block code. But first, when we talk about a block code, there is a notion of length, that is the number of components. This block code is going to be composed of vectors, and the number of components in each vector is the parameter, which is called the length. So, a binary block code of length n is simply any subset of f2 to the n. For example, if n is 5, then there are 2 to the 5, 32 n tuples, 5 tuples. If you pick any subset of them, then you are justified in calling that to be a code. Okay, now you might be somewhat surprised with this definition, but just keep in mind that I did not say, I did not tell you that it would be a good code. Okay. So, for example, and from a just a pictorial, abstract pictorial depiction. So, let us say that this represents the set of all n tuples. So, this entire picture here represents the collection of binary n tuples. So, the red vectors here are the code words, and the green dots are the other n tuples. So, these are the subset that form the code, and so the elements of the code are called code words. So, you have in this particular case 5 code words. Now, just a quick perhaps I will reserve, I was going to talk about error correction, but intuitively you can see that if you transmit a code word and during transmission it is corrupted and what you receive is a neighboring n tuple, then by going back to the nearest code word you can correct errors. Okay, so, that very quickly is how an error correction code works, at least in an abstract sense. But I want to end this lecture by talking about some parameters of a code that we will need in the next lecture. Okay, so there are 4 parameters of a code C which I use to actually judge both to identify as well as judge the efficacy of the code. One is the size of the code, and that simply is the number of code words in the code. The other is the length, but I have already told you about what it means to talk about the length. So, that means that in a code all the vectors have the same number of components, and that common number is the length. Okay. The rate of a code, now that is defined as the log to the base 2 of the size of the code divided by n. Okay. So, that turns out to be a measure of how much information is transmitted or how much uncertainty is dispelled when you actually receive the code over the channel and decode it correctly. Okay. So, that is a definition that actually comes from information theory, and I think you will get a better feel for it once we look at examples. So, I will not spend time on that for now, and we will close with just the 4th and last parameter. So, the last parameter of the code is the minimum distance, and the minimum distance, the notation for that is dmin of C. This is script C standing for the code. Dmin of the code is the minimum distance between a pair of distinct code words. That is, you list all your code words, all of them are n tuples, binary n tuples, and you look at the ones that are closest together in terms of Hamming distance, and that minimum Hamming distance is the minimum distance of the code. Now, it is not too hard to see why that would be important in error correction, because so for example, if you look here, here are the code words, and you can see that if noise perturbs a code word and the noise is noise arising from the channel, then you will start with a code word, but end up with an n tuple. And if the code words are too close to each other, then it will be hard for you to tell which code word it came from. In fact, it may be possible that noise would drive you from one code word to the next if they are too close. So, you would like to keep them separated, but acting in opposition to this is your desire to send a large amount of information. So, that is the rate of the code. So, the rate of the code grows up with the size of the code. So, these two act in opposition to each other. One says that I want to put more and more code words into this space in order that I can send more information. The other says, well, wait a minute, I want to correct errors, and for that I would like to space the code words apart. Okay. So, there is a trade off. So, what you would like to do in coding theory is build code words which for a given size are as far apart as possible, or for a given distance, minimum distance between code words, have as large a code as possible. Okay. But all of this will become clear in the next lecture when we look at some examples or become clearer. So, just to recap, what we did was I gave you a course outline, and then I pointed out what some of the resources that are available to accompany this course are, and then we looked at basics in terms of how to deal with binary vectors, Hamming weight, Hamming distance, and then we defined an error correcting code. Okay. So, with that I would like to close. So, look forward to seeing you in the next class. Thank you.